Lesson 3.3, Day 2. Please complete our summary slide, answering the question, what did we learn yesterday, or what did we learn in our previous lesson? Our learning target says I can identify rate of change / slope. Our essential question says, how do you find the rate of change from a graph or a table? And we have one vocab word, and that's rate of change. Rate of change is the same as the slope of a line. So we've already worked with slope. So I'm just going to remind you what we've already worked with. So slope is the steepness of a line. And we also define slope as rise over run. We also used a slope formula where we subtracted our y-coordinates on the top of our fraction and subtracted the x-coordinates on the bottom. So now we're going to work with rate of change, and the rate of change is how much one variable changes in regards to another. So how much one variable changes in respect to another. And what we're going to use to represent this rate of change is a triangle called delta. Delta represents the change. Delta is just a Greek symbol. So delta y means the change in y, and delta x means the change in x. So the change in y, if you see in the slope formula, it should make sense. You find the change by subtracting two things, and then the change in x, same thing, you find by subtracting two things. Okay, so change in y divided by the change in x, just like the slope formula, just like rise over run. So looking at this table, remember a table has an x column and then a y column. So we are just going to find the change in y and divide it by the change in x. So here are my y values. How much is it changing going from one to the next? So from 59 to 118, to figure out how much it changes, I can subtract them. So it's changing $59 because I'm looking at my label. Then I switch over here to my X column. How much is that one changing? That one's just changing by 1. So use the table to find the rate of change and explain its meaning. 59 divided by 1 is 59. So it's $59 per video game. That's what it means based on the labels in the table. Next table, change in y divided by change in x, y coordinates. Now we're talking about the area of a tiled surface. So if we go from 48 to 96, how much does that change? I can subtract, and it changes 48. Looking at the label in the table, it's 48 inches squared. Now switching to the x coordinates, this one you can probably tell without having to subtract and write it out, it's changing by going up 3. 48 divided by 3 is 16. And if I look at my labels, it's 16 square inches per tile. So they're just talking about the number of floor tiles and the area of tiled surface. So how much does each tile cover? All right, now we're on to some graphs. Now, this graph is asking us to find two different rates of change. 1995 to 2000, and then 2000 to 2005. Okay, so for the first one, 1995 to 2000. So this is the piece of the graph that I'm talking about. So for this piece of the graph, so from 1995 to 2000, the change in y divided by change in x. So to figure out how much y changes, these are your y coordinates. So we're subtracting 9.0 minus 8.1. So that's 0.9 or 9/10. And 1995 to 2000 is a 5-year interval. So if I divide this, it's not a great number. It's 0.18. Looking at my labels, we're talking about departures in the millions per year. So airline departures. So this is millions per year. So really, if that's millions, so millions, think about what millions looks like. So let's see, 0.18 million. So if this is a comma, so it's not quite 1 million. Okay. So it's 180,000 per year. Okay, next interval. Switch my color. Now we're talking about this one. So change in y over change in x. And this one's going from 9 to 9.9. So if I subtract those, I get the same thing. So 0.9 divided by 5 again, because it's still a 5-year interval from 2000 to 2005 here. Oops. So here to here. Okay, so again, if it's 0.18 million, it's not a million. So 180,000 per year. Now there was a final question being asked. Is it a constant? Because our values stayed the same, we can say yes, it is a constant. So this is linear because it's a constant rate of change. So that's what linear means. If the rate of change stays the same, it's a straight line. And you might have been able to tell just by looking at the graph, but doing the math verifies that. Okay, next one. The rate of change from 2002 to 2004. So if we do the change in y divided by change in x, 8.9, so it went from 7 to 8.9. So that's an increase of 1.9. It's important to recognize the graphs we've seen so far were both increasing. They're not always increasing though. So it could be something that's going down where the rate of change is a negative number. So you have to be careful. And this interval is 2 years, from 2002 to 2004. So if I divide this one, I don't get a great number again, 0.95. And again, it's millions. So then this is really 950,000 passports per year. Okay, switch my color. Next interval, 2004 to 2006, so this piece. And I think you can tell from looking at the graph, this is a steeper slope. So this is not going to be linear. This one's changing from 8.9 to 12.1. So if I subtract this one, I get 3.2. And it's still a 2-year interval. So this one is 1.6 million, so that means 1.6 million. So that's 1,000 million. And again, it's passports per year. And then to answer the question about is it a constant, this one is no. It's not constant because we got different values. Constant means that it stays the same. When something is a constant, it's not changing. Okay, so be careful with your graphs. When you're finding the change in y and the change in x, remember to use subtraction and then ask yourself, is it a positive or negative? Is this increasing or is this decreasing? All right, next up, we are just going to determine if each function is linear. So that means we're looking for the rate of change and we're figuring out if it's a constant. So change in y over change in x, is it a constant? So we look at each of these intervals. The change in y from 6 to 12 is 6. 12 to 18 is also 6. 18 to 24 is also 6. So all three of them are 6. And then x each time is changing by 1. So this is a constant rate of change because each interval is 6 divided by 1. So all three of these are the same. So yes, it's linear. It has a constant rate of change. If one of those was different, it would not be linear. So you have to be careful and make sure you find all of the intervals. Okay, our next one, this one you might find to be a little bit harder to figure out. So looking at these values, it went from 5 to 1, so it's going down 4. Then it went from 1 to -4, that's down 5. And -4 to -10 is down 6. You could use a number line to help you, or you could subtract them to figure out how much they're changing. Then over here, -10 to -2 is actually going up 8. It's getting closer to 0. -2 to +6 is also up 8, and so is 6 to 14. So when you look at these, change in y over change in x, -4 over 8, -5 over 8, -6 over 8. So you might think, well, it's a pattern, that's a good thing, but these are not equal to each other. So this is not linear. So I'm going to say nonlinear, and my reason is because it doesn't have a constant rate of change. Be careful because just being different numbers doesn't guarantee that it's not going to be a constant rate of change. So just for example, if this one looked like -4 over 8, and then -5 over 10, and then -6 over 12, that would have been okay. So you have to be careful. So it's not like you can stop right here and say, oh, those are different numbers, it's not going to be a constant. You've got to check the other numbers as well, because it's the change in y divided by the change in x that has to be a constant that determines if it's linear. And that is our last example. So be careful, check each interval, and it should be good.